Hi dear students, the last class we discussed the passage of AC through LC and RC circuits, and we also discussed what is the power, what is the impedance, and also the phase angle phi of each circuit. And today, as a continuation of this previous discussion, we start the alternating current through an LCR circuit. This is very important topic in the university examination point of view and also for the competitive examination point of view. An LCR circuit consists of an inductor, this L, and C stands for the capacitance, and R corresponding to a resistor connected to an alternating voltage source. This is the inductor L, C, R. Here also we address this question, that is, what is the impedance of this LCR circuit, and what is the phase angle, that is the angle between the current and voltage in the LCR circuit. We know that the phasor diagram of the inductor is on the x-axis. We plot the current. In inductor, the voltage leads the current. The L stands for the leads. That is, on the x-axis we plot, this is a VL. There is a phase difference between the voltage and the current by an angle pi by 2. In the capacitance, the voltage lags behind the current. Therefore, there will be a 90-degree phase difference between the voltage and the current. The current is plotted on x-axis. Since the voltage lags behind the current, therefore we represent the voltage B.Sc in the negative y direction, and in the resistor both the current and the voltage both are along the same direction. There is no phase difference between the voltage and current. There is no lags of the voltage or the current in the R circuit, that is the resistor circuit. If we plot the phasor diagram of this LCR circuit, then on the x-axis that we plot the current, and since the voltage leads in the inductor, that we will write here, and is on the positive y-axis. Since the voltage lags behind the current in the capacitor circuit, therefore that we will write in the negative y direction, Vc. Fine. In the last lecture, we used the notation that the voltage represented by E, that is EL, is the voltage through the voltage across the inductor, and EC is the voltage across the capacitor. The present circuit is a series LCR circuit, and if I draw the correct phasor diagram of this series LCR circuit, that is, I will plot here. On the x-axis we have the current, and on the y-axis we have to plot the voltage. Here, since the voltage through the inductor leads the current by an angle pi by 2, then that voltage is represented along the positive y direction, and the voltage across the capacitor lags behind the current. Therefore, that has to be plotted along this negative direction. Instead of that, what I will do is the same the voltage that if you represent as a minus EC, that I would like to plot along the same y-axis by considering that EL minus EC. Okay, that means I represent both EL and EC on the positive y-axis by taking the sign minus with the EC. The voltage across the resistor, that is ER, that both the current and voltage are along the same direction. Now the net voltage, that is the applied voltage, E is equal to E0 sine omega t. Then the net voltage in the circuit, that can be represented by this E. This is the net voltage of the circuit, and the angle between this voltage and the current, that is this angle phi. Then if you project this net voltage in this way, this is nothing but this EL minus EC, this length, and the opposite side, that is this one, this is nothing but our ER. Fine. Now using this phasor diagram, we will solve the impedance in the circuit. That is, to do that, we will take the hypotenuse square. E square is equal to this adjacent side square plus this opposite side square. That is a hypotenuse square means we use the Pythagoras. E r square plus EL minus EC all square. Okay, that is this E square. ER means is nothing but I into R all square plus EL means I into XC. EC means I into XL. This is into I into XC, the whole square. E square is equal to I square into R square plus, if you take the I square from this term outside, this will be XL minus XC whole square. Then if you take the I square common outside, this will be R square plus XL minus XC all square. The impedance, that is E by Z, or I will write here E square by I square, then the above expression can be written as XL minus XC all square plus R square. This E square by I square, if I take the square root, this will be E by I, this will be root of XL minus XC all square plus R square. This E by Z, E by I, that is nothing but the impedance, because V is equal to I into R and R is equal to V by I. That is E by I, that is this quantity is nothing but the total resistance offered by the circuit, that we call as an impedance. That is E by I is nothing but total impedance, that is equal to root of XL minus XC all square plus R square. Or here we can write this impedance in terms of the omega and L, and also in the omega and C. XL is nothing but L omega minus XC means 1 by C omega, the whole square plus R square. Fine. This is the impedance of LCR circuit. That means this is the total resistance offered by the LCR circuit to the flow of AC. Fine. Now next our task is to determine what is the phase angle phi. That is, if you look at this picture, here you can write that is tan phi. Tan phi is equal to opposite side, that is EL minus EC, divided by adjacent side, that is ER, that is I XL minus I XC divided by I into R, that is, this is equal to I take outside XL minus XC by I into R. This is XL minus XC by R. From this you can easily find out the value of the phi, that is the phase angle. Thus we can write this tan phi is XL minus XC by R, or L omega minus 1 by C omega by R. This is the phase angle. That is, one can easily find out phi is equal to tan inverse L omega minus 1 by C omega by R. Now, what is the power factor cos phi? If you come back to this picture again, this cos phi can be written as, cos phi means adjacent side, that is ER, divided by hypotenuse, that is E, ER by E, that is I into R divided by E means I into Z. This I and I cancelled. R by Z is the cos phi. Then if you substitute the value of Z, this will be R by Z, that is, just now we have derived total impedance of the circuit, that is XL minus XC all square plus R square. Then if I substitute instead of XL, that is L omega minus 1 by C omega square plus R square. This is the cos phi, that is the power factor of the LCR circuit. Fine. These equations are quite important because in the competitive examination, a lot of questions have been asked so far. Now let us come back to this tan phi once again. Tan phi is equal to XL minus XC by R, or L omega minus 1 by C omega by R. We will analyze the different case where this XL, that is the inductive reactance, is greater than the capacitive reactance, when the capacitive reactance is equal to the inductive reactance, or when the capacitive reactance is greater than the inductive reactance. We will see what is the effect of this phase angle. The effect of this phase angle means if the phase angle is positive, then the voltage leads the current. The phase angle is positive only when this XL is greater than XC. Then that case, in the case of the inductor, where the voltage leads the current, the same way here also in the LCR circuit, if the inductive reactance is greater than the capacitive reactance, then the voltage leads the current. And in the reverse case, that is, if XL is less than XC, then XL is a smaller quantity and XC is a larger quantity. The numerator is negative, the tan phi is negative. Tan phi is negative means where the inductive reactance is smaller and the capacitive reactance is larger. Then if the capacitive reactance is larger, the capacitive network or the capacitive circuit, where the voltage lags behind the current. Therefore, in this LCR circuit also, if XL is less than XC, where the voltage lags the current. Fine. Then if XL is equal to XC, then the numerator of this tan phi, that will be 0. Then tan phi is equal to 0. Tan phi is equal to 0 means the phase angle phi is equal to 0. If phi is equal to 0, there is no phase difference between the voltage and the current. That case exists in the case of pure resistive network. Then we will say this LCR circuit is a pure resistive circuit when this XL is equal to XC. Fine. Now let us analyze each of the case one by one. That is the first case. The first case is we know the tan phi. Tan phi just now copy here. That is XL minus XC by R, or L omega minus 1 by C omega by R. Fine. Now if XL is greater than XC, first case, then if you look at this expression, that is where that is this L omega, XL greater than XC means L omega is greater than 1 by C omega. In such a situation, the tan phi, that is if you look at this expression, XL is greater than XC, then this is the positive. Tan phi is equal to positive. If tan phi is positive, that is the phi is positive. Fine. If phi is positive, to know which one is lagging or which one is leading, if phi is positive, just look back to this XL greater than XC condition, and in the XL, in the case of the inductor circuit, here the XL is greater, therefore in the case of the inductor circuit, here the voltage leads and the current lags. Fine. Or in another way, current lags behind the applied EMF. Now let us go to the second case. That is, in the second case, if XL is less than XC, that is L omega is less than 1 by C omega, then our tan phi, that is this quantity, if XL is less than XC, then numerator will be the negative. If the numerator is negative, tan phi is negative. If tan phi is negative, means phi is negative. That is, tan phi is negative, which gives phi is negative. The phi is negative means which one is leading or lagging in the LCR circuit if phi is negative. That is clear if you look back to this condition. If XL is less than XC, here the greater quantity is XC, the smaller quantity is XL. Greater quantity XC means here in the case of the capacitor circuit, where the voltage lags behind the current, or the current leads a voltage. That is, here we will write, if the tan phi is negative, the phi is negative, then this arises because where the capacitive reactance is larger, then in the capacitor circuit, the voltage lags behind the current. That is, voltage lags behind the current. Or we can say the current leads the voltage. Current leads the voltage. Fine. Now let us come to the third case. That is, if the inductive reactance XL is equal to the capacitive reactance, then our tan phi, that will be 0. Fine. If tan phi is equal to 0, then phi is equal to 0. That is, the phi is equal to 0, that is in the case of the pure resistive network, where we have seen that both the current and voltage both are in the same direction. No phase difference between the current and voltage. Okay. Here no one is lagging or leading, all are in the same phase. That is, the current and the voltage are in phase with each other. Fine. Okay. There is here no phase difference. Let us check what is the value of the current in the LCR circuit if this third condition is satisfied. XL is equal to XC. That is, the current in the LCR circuit is defined by E by Z. Z is the impedance, that is XL minus XC whole square plus R square. Then if XL is equal to XC, here this I will be E by, in the numerator this term goes to 0 because XL is equal to XC. Therefore this will be 0 square by R square is nothing but E by root R square, means that is nothing but E by R. If you once again look to this expression, that is the current in the circuit, this will be maximum if the denominator is minimum. The denominator gets a minimum value only when this XL is equal to XC. That is, when XL is equal to XC, the Z is minimum, therefore the current I is maximum. Fine. That is, let us say if XL is equal to XC, this value of current, that is I is equal to E by R, is the maximum current that will flow in the circuit. Fine. അതായത് ഈ സർക്യൂട്ടിൽ കൂടി, ഈ LCR സർക്യൂട്ടിൽ കൂടി മാക്സിമം കറണ്ട് ഫ്ലോ ചെയ്യുന്നത് എപ്പോഴാണെന്ന് ചോദിച്ചു കഴിഞ്ഞാൽ XL ഈസ് ഇക്വൽ ടു XC എന്ന് പറയുന്ന കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുമ്പോഴാണ്. ഓക്കെ, അപ്പോൾ എങ്ങനെയാണ് XL ഈസ് ഇക്വൽ ടു XC എന്ന് പറയുന്ന കണ്ടീഷൻ സാറ്റിസ്ഫൈ ചെയ്യുക? How this condition is satisfied, or how we can achieve this condition in an LCR circuit? That is, if XL is equal to XC, then actually this is a XL means L omega, XC is 1 by C omega. The voltage, that is E is equal to E0 sin omega t. This omega is the frequency of this applied external voltage. XL is equal to XC, the denominator, that is impedance, become minimum and the current in the circuit will become maximum. Then that condition is known as a resonance condition. Okay, we will call that is at this condition, that is when XL is equal to XC, the circuit will be in resonance with the supplied voltage. Fine. Now I will explain what is the phenomenon of the resonance. We have the expression for the current in the LCR circuit, that is E by Z. That is, we can write this Z is root of XL minus XC whole square plus R square. That is, when XL is equal to XC, we have seen that this denominator, this value went to 0, and this will be E by root of R square. This is E by R. That is, the denominator is decreased and the current increased. Therefore, when we can say when XL is equal to XC, the denominator is nothing but the impedance. That is, Z is, the impedance means the Z is minimum and the current is maximum. Okay, there is a maximum amount of current flow through the circuit when its capacitive reactance is equal to the inductive reactance. this L omega is equal to 1 by C omega. That is, we can say at a resonance, the XL is equal to XC. Okay. Now what I am going to explain is, by tuning this omega, resonance conditions can be obtained. Then what is the value of the omega? What should be the value of this frequency? That is, to obtain the resonance condition in the LCR circuit and hence to flow a maximum current in the circuit. To find out the expression for that particular value of the frequency, or that we call the resonance frequency, we do this following. That is, XL is equal to L omega, XC is equal to 1 by C omega. If I bring the omega to the left side, this will be omega square. Then I bring the L right side, this 1 by LC. That is, this omega is equal to 1 by root of LC. This is the value of the omega. This omega is the frequency of the applied voltage. Or in another words, we can write this is a 2 pi f. Omega is nothing but 2 pi f. This is 1 by root of LC. That is, here we can write f is equal to 1 by 2 pi root of LC. That is, at this frequency of the applied voltage, the impedance in the circuit becomes minimum and hence a maximum current flow through the circuit. This is called a resonance frequency. That is, we can define the resonance frequency in this way. The frequency at which the impedance of the circuit becomes minimum and therefore the circuit currents become maximum is called the resonant frequency. Fine. Now, the series LCR circuit is used as a tuning circuit. Why this series LCR circuit is used as a tuning circuit? That is, I will explain now. That is, we have two types of circuit: series LCR circuit, that is there in your syllabus. The one, there is a parallel LCR circuit that can be used as a rejector circuit. But in your syllabus, you don't have to study the parallel LCR circuit. You have to study only the series LCR circuit. This series LCR circuit is used as a tuning circuit. What is a tuning circuit? If you have a radio station, that radio station have a programs at a particular frequency, let me, that is a 92 megahertz. That is, from the radio station, this wave, the broadcasting frequency is the 92 megahertz, and this is your radio, and this radio consists of a series LCR circuit. The F is the frequency of the broadcasting frequency, and the series LCR circuit in your radio that has a particular frequency. Then to receive this signal, your radio will receive the programs that's broadcasted by this station only when the frequency of the tuning circuit of your radio, that is given by f is equal to 1 by 2 pi root LC, that matches with the frequency of this broadcast. Okay, there is a frequency of this wave must be matched with the frequency of this series LCR circuit. The frequency of this broadcasted wave, that cannot be changed by us. To match with the frequency of this broadcasted wave, what else we can do? The value of L that we used to the series LCR circuit in the radio, that we cannot be changed, because it is not possible to open the radio and to change the value of L according to the frequency of the wave. Then next we have the option C. C is the capacitance. Capacitor, the value of the capacitor used in the LCR circuit. There is a parallel plate capacitor. We know the expression epsilon 0 A divided by D. Okay, here the area of the capacitor plate is constant, but the value of D can be adjusted. You might have seen the knob on the radio in this picture. By rotating this knob, actually what you are doing is you are changing the plate separation between the capacitor plate. That is, you are actually varying the D. By rotating this knob, you are actually varying the distance D. If the value of D is changed, then the capacitance will changes. Once the capacitance changes, according to this expression, the frequency will also change. When the frequency changes and matches with the value of this broadcasting frequency, 92 megahertz in this example, when these two frequencies, that is the frequency of this receiver circuit, when matches with the frequency of this wave, then the current in the LCR circuit become maximum, because here the resonance condition is achieved. It's the frequency of this circuit exactly matches with the frequency of this wave, then there is a frequency matching. When the frequency is matched, then a maximum current starts to flow through this LCR circuit, and at the meantime the impedance become minimum and the current become maximum when this resonance condition is achieved, and this maximum value of current flow through the LCR circuit, that is through your radio, that is through your tuning circuit. Then you will get the programs that is broadcasted by the station. Fine. In this way, the series LCR circuit is used as a tuning circuit. Now let us come to the another important point, that is, what is the variation of the current with the frequency of the applied voltage. Fine. That is, in your LCR circuit, the applied voltage is E0 sine omega t. This omega is nothing but 2 pi f. This, by varying the frequency of this applied voltage, you can also obtain a resonance condition. That is, you can see a maximum value of current flowing through this LCR circuit. That is, now we study the variation of the current with the frequency of the applied voltage in the LCR circuit. If you refer this figure, that is, the frequency is along the x-axis and the current that is flowing through the circuit is along the y-axis plotted. Then this is the curve obtained. How this curve is obtained? See, we have a circuit where the value of resistance is R and the inductance is L, capacitance is C, and the applied voltage is this one, 2 pi f. Then at a resonance condition, then the expression for the current is given by I is equal to E by R. For a particular value of the applied voltage, that is, if you come back to this graph, that is a particular value of the frequency, that is this line, let us say maybe 90 hertz or 90 megahertz, whatever it may be. For this particular value of the frequency, we called mu 0. We can represent this as a 2 pi mu 0, where mu 0 is a resonant frequency. That is, this f we can write as a resonant frequency mu 0, 1 by 2 pi root LC. This mu 0 is the resonance frequency, and at this particular value of this resonance frequency, once of frequency is fixed, then if you vary this resistance, okay, then the current will change. When R is smaller, current is larger. When R is larger, then current is smaller. Here you see, that is, when if R is high, If R is high, then current I is smaller. This is for a particular value of the frequency. That is the picture here. When R is high, the current is this value, smaller value. Now in the second case, if R is small or R is low, current is larger. Current I is larger. That is noted here. When R is this one, when R is low, then the current is larger value. Fine. Here, one more point that I would like to emphasize here is this one. That is, here the sharpness of this peak is more sharper than this peak, and the sharpness of the peak depends on the value of the resistance. Okay, this I want to mention here. That is, this graph, you note down that this graph is a variation of current with the frequency of the applied voltage. Okay, and the point that we obtained from this discussion, that is, sharpness of the peak depends on the resistance R. Next, we discuss the quality factor. The quality factor is actually the measure of the sharpness of LCR circuit. We discussed the sharpness of the LCR circuit, and this is the measure of the sharpness. Or this can be defined as the ratio of the peak energy stored in the resonator in a cycle of oscillation to the energy lost per radiation of the cycle. Larger the value of the quality factor, the larger will be the sharpness of the resonance. Okay, that is, you will get a perfect hearing experience if the radio has a LCR circuit with a larger value of the Q factor. For in our tuning circuit or in our radio, if the Q factor is larger, then we will get a clear hearing experience. It is a perfect hearing experience will be there if the LCR circuit has a larger value of the Q factor. The another interpretation of the quality factor is this one. Shortly, the quality factor is a quality factor of a component. Okay, this is a quality of a factor of a component. That is, for example, for an inductor, the Q factor is how an inductor has pure inductive reactance comparing the resistance embedded into the inductor. Okay, that is quality factor is a ratio of the pure inductive reactance to the resistance. It is a measure of how an inductor has a pure inductive reactance comparing the resistance spread into the inductor. That is the ratio of the, for an inductor is there, then the ratio of the inductive reactance and resistance of that inductor. That ratio is the quality factor. That is, all other phenomena are the side effect of the Q value. Okay, actually, in the same way we can also define the Q value for the capacitor also. That is, a capacitor, the quality factor of the capacitor we can define like this. How a capacitor has a pure capacitive reactance compared to the resistance spread or embedded into the capacitor. This defines the quality of that component. That is, the Q factor is a quality factor of a component. For a capacitor, this is the ratio of the capacitive reactance to the resistance, that is the R. Fine. This is the quality factor of the capacitor. This is the quality factor of the inductor. Another simplest example, I can define the quality factor. This I can calculate the quality factor for milk, compare the milk quantity and the water quantity added to the milk. If I have a milk in a bottle, in a glass, then I can calculate the quality of the milk by using this expression. That is the milk quantity divided by water quantity. Okay, if more water is there, then the quality is bad, quality is low. If more capacitive reactance is there, then the quality factor of that capacitor is very large. If more inductive reactance is there, then the quality factor of that component, that is here the inductor, is large. In this way we can define the quality factor. Quality factor that can be defined as a voltage magnification factor at resonance. That is, how this can be experimentally measured. This can be easily measured by using this expression, that is, measure the voltage across the inductance is voltage across inductance divided by voltage across resistance. That is VL by VR, that is I into XL divided by I into R, or this can be written as XL by R. As I mentioned earlier, if the quality factor of the inductor means this is the inductive reactance divided by the total resistance. Fine. Or in other words, we can write this quality factor Q is equal to XL means L omega by R. That is, here omega is the resonant frequency, that is omega 0 we denote, that is omega 0 is a frequency at resonance. Fine. Then what is the quality factor of a capacitor component? That we can also define like this: voltage, that is, this is another definition. We can define the quality factor in this way, that is, measure the voltage across the capacitance, then divide it by the voltage across the resistance. Fine. That is VC by VR, that is I into XC by I into R. This is XC by R, or this is 1 by RC omega, because this XC is 1 by C omega. This is also omega naught, resonant frequency. Fine. I can write this Q factor in another form, that is 1 by RC omega 0 is there in this expression. Then instead of that omega 0, we know that XL is equal to XC, and XL is L omega 0 is equal to 1 by C omega 0. From this omega 0, I can write 1 by root of LC. That is, this omega 0, that is 1 by root LC, I substitute instead of this omega 0. Then into this expression, instead of that omega 0, I will write this is a 1 by root LC. Fine. That is, one can write the equation of the quality factor in this way also, that is 1 by R into this C and root C were cancelled, 1 by R into root of L by C. This is the expression for the quality factor. We can define the power in LCR circuit. That power in the LCR circuit can be defined as, let us say, we have always calculated the average power, that is voltage into current, that is RMS value of the voltage into RMS value of the current into cos phi. The cos phi we have already defined, that is cos phi is nothing but R by Z. This Z is equal to root of XL minus XC all square plus R square. That is, this can be written as ERMS into IRMS into R by Z. Fine. According to the question, you can modify the equation for the power factor and also the average power. Okay, these are all the discussion about LCR series circuit. This LCR series circuit is used as a receiver circuit or the tuning circuit. To get an idea about the problems in this session, we will do just one problem. This is a question, that is, in the series LCR circuit, the instantaneous voltage and current are given by this expression. E is equal to 70.7 sine 500t plus 30 degree volts, and the current I is equal to 2.83 sine 500t plus 30 degree amperes. Find the value of R, C given L is equal to 0.5. Okay, our aim is to find out what is the value of resistance, what is the value of the capacitance in the circuit. Here, to solve this problem, first we rewrite the value of the voltage given, that is 70.7 sine 500t plus 30 degree, and the current I is equal to 2.83 sine 500t plus 30 degree. If such kind of problem is asked, then first we have to see what is the phase difference between this voltage and current. If you check these two equations, then this has the general expression E is equal to E0 sine omega t plus phi. Fine. Then if you check the phi, the phase angle, that is the voltage has the phase angle 30 degree, current has the phase angle 30 degree. That is, in the given LCR circuit as mentioned in the question, the phase difference between the voltage and the current, that is phi, that phi, let us write the phase difference between the voltage and the current, that is in the circuit, that is 30 degree minus 30 degree, both have the phase angle 30, that is equal to 0, which means there is no phase difference, that is both the current and the voltage are in phase. Okay, there is no phase difference between E and I, both are in phase. Now you think about where is the phi is equal to 0 in an LCR circuit. That phi is equal to 0 when the LCR circuit becomes only when XL is equal to XC. That is, you think about the expression for the phi. That is, if you remember the phasor diagram, that is, we had this phasor diagram. Here, this was our net voltage and this was our EL minus EC, and this was our ER, and this is the angle phi. Then tan phi is equal to EL minus EC divided by ER. This is finally we obtained IL and EL and EC replaced by IXL and IXC. Then both I cancel in the numerator and denominator. This was XL minus XC divided by R. When XL is equal to XC, the numerator went to 0, therefore this was 0. This tan phi was 0 when XL is equal to XC. That is, we can write this is if XL is equal to XC, then our aim is to calculate this resistance and the capacitance. When XL is equal to XC, what was the impedance? That was root of, that is XL minus XC all square plus R square. Then when XL is equal to XC, this is root of 0 square plus R square, that is root of R square is nothing but R. Is Z is equal to R. Just calculate the impedance, that the value of the impedance is nothing but the value of the resistance in the circuit. Okay, to find out the value of R, just to find out the value of Z. What is the Z in the circuit? Impedance, that is, we know that expression for the impedance, that is resistance is nothing but voltage by current, that is the impedance is E0 by I0. E0 is given, that is, if you look back to this expression, this is your E0. E0 is equal to 70.7. 70.7 divided by, what about I0? If you again look back to this expression, that is here, this is the value of the I0. Fine, that is 2.83. Okay, that is Z is equal to, if you divide these two quantities, this will approximately 25 ohm, because it is mentioned that this voltage and the currents are in the voltage is in volt, current is in ampere. Therefore, the unit is Z, or the R is equal to 50 ohm. Now we answered the first question. The second question was, what is the value of the capacitance? Then to find out the value of the capacitance, we came to know that the phase difference phi is equal to 0 and XL is equal to XC, that is L omega is equal to 1 by C omega. That is, from this we can write the capacitance C is equal to 1 by L omega square, that is equal to 1 by, what is the value of the L given in the question? That is, yes, the value of L is given here, 0.5 Henry. 0.5 Henry into omega. What is the frequency omega? Then for that again you compare the standard equation, that is here, this omega t means 500 t, that is omega is equal to 500, that is 500 square. Fine, if you do this calculation, then you will obtain C is equal to 8 microfarad. Okay, please try to do a lot of problems, because a lot of problems have already been asked in the various competitive examination and also in your university examination. Thank you very much.